Welcome everyone to the Area Research Committee webinar that we have prepared for you all today. It's an exciting talk that we have scheduled for you, and we're looking forward to kind of jumping right in and giving our speaker the opportunity to share what he's got for us. For the purposes of our talk today, we're really focused a lot on interoperability. This talk is really important to all of us because it kind of shares the ways in which, from an industrial AR perspective, we really can look at interoperability and use it to kind of adapt and transform our workforce and our industry. So with that, I am very privileged to introduce at a brief level our speaker. I'm going to let him do his formal introduction when he starts. But happy to really kind of turn this over to Dr. Bill Bernstein. So Bill is an amazing colleague who spent a lot of time working on all of these pieces and has a lot to say about interoperability. So I'll hand it over to you, Bill, to let you introduce yourself and share your presentation with us today.
All right, thank you so much. Just a quick check that you can see my slides. Looks like you can. Yeah, it's an honor and a privilege to, I'll say, be back with the area. I was pretty active when I used to lead a project group at the National Institute of Standards and Technology in the US, which focuses on implementing and testing standards in a government lab. I led a group there that was really focused on visualization for manufacturing data, where we used AR as just one tool for lightweighting models. About 4 years ago, I transitioned over to my home state of Ohio at the Wright-Patterson Air Force Base. And I work for the Air Force Research Laboratory. Specifically, I'm within the Materials Manufacturing Directorate. And you can see my division, my home division on the slide there. Currently, I lead the Advanced Manufacturing Technologies portfolio, which really focuses on maturing manufacturing tech forward. And as you might expect, extended reality is a primary technology to which there's plenty of work, plenty of investment active right now. And I don't think there's any shortage of science and technology gaps that we face as a group, and we're trying to close those gaps moving forward. My talk today is really it was based off an invitation that I really appreciate from the area leadership. We recently published a position paper through the American Society of Mechanical Engineers, and I'll go through that a little bit to position the talk. About what we believe to be really a key challenge for scaling industrial augmented reality systems, and that is this notion of interoperability. And we kind of categorize interoperability into two main modes, one of which is the data itself, the data interoperability that we call, and then also kind of a system level interoperability as a source of tools within a traditional tool chain that you might see implemented across industry that creates all sorts of problems, all sorts of loss of information. And the main thesis of this talk, and I'll just give you the bottom line up front, is many of the issues that manufacturing interoperability deal with are, in my opinion, and this is the thesis of the talk, are almost identical to the same problems that that the industrial augmented reality community faces. And that if the two merge together, those communities and also the techniques and methods to improve interoperability, I think we'd be able to accelerate progress in this space. Before I officially begin, I just want to note that I have the question and answer tab open live. So feel free to place any questions in there to stop me, and I'd be happy to address it. I also want to mention that the talk itself has been cleared for public release. There's a whole lot of other stuff that we do across the Air Force that relates to industrial augmented reality that I'd be happy to answer any questions if people have specific interests in. Let's say I know that one of the panelists is very interested in AR for thermal spray, as an example. We have a pretty significant program in that area. So at first, I just want to mention what our division actually does in the couple slides here. So we are the manufacturing authority across Air Force Research Lab, which means that we gather demand signals from all across our Air Force science and technology needs, not just, let's say, metal structures, composite structures, but also things like what we call mission support systems or electronic substrates. And our main work within our division, some folks might have known us as Air Force Mantech from the past, is that we try to mature and scale promising manufacturing technologies that have a clear goal and sight for the Air Force. We recently, about 3 years ago, stood up our own low TRL digital manufacturing research team. I'm going to feature a slide at the end on what exactly that team focuses on. I'm actually a part of that team alongside my more program management side. We serve on various boards across the DoD Manufacturing Innovation Institutes, which is part of the Manufacturing USA umbrella, which is a public-private partnership across the U.S. in expediting a lot of this kind of technological advancement. We see them as strong partners and larger funded efforts. An interesting fact is our division is actually the primary executive agent for Defense Production Act Title III. So I imagine a lot of folks on the call might not know what that is, but that was the major mechanism that drove a lot of the COVID response across the United States. Think about building up the industrial base for in emergency response or even in capability gaps. For instance, mining rare earth metals is a really key focus of that area right now. And as you would expect, given that we have a full staff of highly trained folks, we provide expertise as needed across different Air Force functions. This is just another view of very similar ideas on the last slide. And I want to direct your attention to the left part of the slide to kind of explain that we really focus on, I would argue, the entire readiness level scale. So we have folks even that's sitting directly next door to me that really heavily focus on the digital manufacturing research, which again, I'll preview a little bit at the end, focusing on those high risk, high value add, long horizon types of technologies, things like robotic autonomy. But then we also have discretionary funding that's expressed in that box that says manufacturing technology that looks at opportunities that might come out of similar research groups like the Digital Manufacturing Research Team that show promise at a laboratory scale and try to scale it up to full production use, whether it be within the defense industrial base or across what we call the organic industrial base, which is just another term for production cells that we control, for instance, things like sustainment depots and so on. And the key primary driver of our division is really focusing on finding that balance between tech, I would say, push and tech pull based on our customers, but then also really trying to reduce cost, proliferate technologies to make it more scalable and more apparent and relevant for the use cases that we're interested in. So this talk is really only going to focus on just one piece of that pie, which is this idea of how do we establish an open digital thread for industrial augmented reality. Now, the word open here is very loaded. What I mean by open is not necessarily fully open source or fully quote unquote free, but rather accessible by I guess a sea of boats, to which you can imagine that they can access things like open data formats, understand the requirements to pass data from one system to another, to promote scale and as fast as possible. So I really like to start with this slide to kind of explain what we're trying to do here. So on the right, we partnered with a team at Lockheed Martin. It's the Emergent Visualization Operations software team down in Orlando, and they develop kind of bespoke augmented reality systems for their workforce. And what you see on the screen there is purposely offset kind of visualization of assembling a control board And the question that they or the problem that they came to us for, and I guess it was a partnership more than anything after many conversations, is that it really takes a whole lot of artistry to properly develop what you see on the screen. And even if you have a similar setup of this operator with another workstation, it still requires a whole lot of hand-holding of the data structures, the views, the texturing, the color mapping, the spatial alignment of what you see in front of you and what the physical against the physical scene. And it is our argument that many of those design decisions of the scene creation should really be described in a way that is computer interpretable, so that you can automate a lot of those decisions to quickly generate that scene, at least a best fit 80% solution, so that at the end, you're not getting rid of necessarily the stack of software developers required to develop a good AR presentation, but rather you are just quickening the scene development. So we look on the left. This can be really described with where the opportunity space lies is in that blue box. So with almost any augmented reality application, there's this sense of capturing the real world, understanding it, and overlaying some kind of domain-specific model to create a XR AR scene presentation. It's my argument that there's a whole bunch of standards that contribute to describing what's in that blue box, whether it be how people behave, the spaces to which they work, the plans, whether they be work plans or inspection plans. If AR-based inspection is an important aspect in your world, and also the materials to which they're actually directed to manipulate within that scene. And what I've noticed, and our team has noticed, is that a lot of the industrial AR work has either through honestly maybe ignorance or just a lack of awareness, has not really leveraged the domain-specific standards that exist, let's say in manufacturing, to be able to seed that scene creation. And that's really what we're trying to achieve, is we're trying to make those dotted lines more solid in nature, meaning more computer interpretable and automated, rather than a lot of human touch labor on the software development side. So we kind of took a step back, and this was about, it was published, 2 years ago. So about 3 years ago, we built a position paper in the American Society of Mechanical Engineers, Journal of Computing, Information Science and Engineering. And the DOI link is there. And I would ask folks to go check it out. What we did is, industrial AR has, specifically in manufacturing, has been studied for quite some time. I mean, we're even citing papers there from nearly 20 years ago, 15 years ago or so. What we did is we said, okay, all these folks seem to be saying very similar things. How can we take a step back and conduct a meta review of the 7 seminal industrial AR papers and build a roadmap to understand where does the digital thread fit into the picture and how we can really approach the problem. And I'll just give you the kind of bang box up front. What we found is the hypothesis to which I started this talk to be true, that much of the problems that many of these papers kind of dive deep into are very, very similar to, quote, realizing the manufacturing digital thread. So let me give you an example of 2 interoperability challenges, and these kind of give a sense of how this paper classifies what interoperability means to at least our group here from a data versus system perspective. So here's an example of, and this is actually a project through one of our partners, Manufacturing Innovation Institute, called Advanced Robotics for Manufacturing. It's the ARM Institute that sits with, as part, kind of an offshoot of, well, not technically, but very similar to an offshoot of Carnegie Mellon out of Pittsburgh, Pennsylvania. And what you see here is an operator who is guiding a robotic cell to conduct a thermal spray process. And actually, there's comms between the AR headset and what the operator is doing and guiding where the robot to start doing work on the workpiece. and then it's actually being passed to a smart algorithm that is then generating a path plan for the robot to go do. To actually build this demonstration, this took, in my opinion, just far too much labor, money, cost, artistry, etc. And the reason is because generating a consistent idea of coordinate systems between how the human understands its input into the physical space against how the HoloLens, in this case, understands its coordinate system against that input from the user you see in slide B, and then of course against how the robot views the coordinate system of itself, meaning its joints and its end effector path. This is just an example of why this is so difficult, is that you're essentially merging 4 or 5 different coordinate systems to accomplish a complex task. And hence, if the way in which we describe spatial datums and coordinates and terms between them, you can imagine a situation where this could, maybe 10, 20 years from now, hopefully it's sooner than that, could actually be positioned autonomously, meaning that it could understand almost outside of its own planning to understand that this input means start here and end here for this particular task. Just something to think about. Secondly, we kind of classify what we call system or model interoperability. And this is kind of typical of sort of passing exchange formats from one workflow, from one software to another, and the inherent loss of information. And this is a massive problem, not only within industrial augmented reality systems, but I would say any kind of industrial workflow where there's a mix of different softwares to which different entities within the organization do their job and have difficulty in having those things sing well together. So this is just a simple example where you might see that. Let's say you're trying to create some kind of AR scene definition of an animation, and you want like different assemblies to kind of work together within, let's just an example, the Unity engine. In the perfect world, you would get the authoritative model from some kind of native CAD. I actually don't remember what the screenshot of that particular example is in the top left. And then you need to take some kind of exchange format, let's say step, to get information out of that native CAD. And that little yellow triangle is supposed to infer that you lose information, right? And you place it into, let's say, an animation definition software, and you get out a DAE structure, a collada, structure. And even that, inherently, you lose information because you weren't working directly within that exchange platform or that exchange format. You send it into Unity. Then what you have to do is then pull in a whole bunch of information that was actually defined back in the assembly definition through a bill of materials. Those could be Excel files, PDFs, all different kinds of different formats. And where you see that little human boxes is where you need all this human intervention to create some kind of artistry to make an XR scene that makes sense for the user. And I know that many of the folks on the panel here really focus on kind of like, how do we make that interoperable across the different headsets, which is supposed to, which you see that last box on the right with the different logos. Of course, that's an issue as well. But this requires a whole lot of artistry, a whole lot of human touch labor from a software development. So what we did is we went through these 7 papers that I mentioned before. And I'm not going to go through all the details here, but what we tried doing was classify what the main issues were regarding basically the last sections of all these papers, where they talk about, all right, we just reviewed everything that is going on right now in this narrow area. As researchers, here's some ideas of where we should go forward. So what we did is we took all those research challenges that were summarized mostly at the end of those papers. Of course, some of them were at the beginning. And we tried finding commonality between them and building out this table of near-term, mid-term, and far-term research challenges, to which we drew some roadmaps. So we had 2 roadmaps here. The white boxes, gray boxes, try not to really pay all that much attention to it, but you'll see some shared or common themes across what we called data-driven processes, or how we generate the scene, issues or challenges and research opportunities that might exist against more ergonomic based processes that were covered in the papers. And what you see, maybe you kind of get the hint of where I'm going, that a lot of this stuff really has very little to do with actual augmented reality and more to do about the data passing and the data interoperability and the intelligence within the manufacturing environment. So I'll just keep going on based on time. We also did the same for what we called kind of human factors or ergonomics related issues. A lot of hardware challenges and directions forward that are listed in the paper. That's not really the focus of this talk. And kind of the ultimate goal are pretty interesting. For instance, imagine an AR device that's actually just a contact lens where there is no quote unquote human factors. Maybe it's internal human factors of how the eye perceives what kind of signals it's picking up. Okay, so now I'm going to switch themes and I'll come back to those roadmaps because they are relevant for the end. So we have a whole other group of work. And again, the whole thesis of this talk is that things that we're doing in the manufacturing world related to digital thread, connecting data structures, will help scalability for industrial AR. That is the main focus of this talk. The past 3 years, we've really spun up a significant programmatic area within, I would say, modernizing how we pass technical data between organizations, whether that be somebody who's building an aircraft and the Air Force organizations that accept those as good fleet members. And the key notion here is, yes, we're pretty good at trading the technical data that describes the nominal fit, the idealized geometry of what a aircraft should be. We are not so good at basically feeding back what the aircraft actually is. And anybody that has worked in aerospace knows that the moment that you fly a plane, it is a different plane. And the second time you fly it, it's a different plane after that. And there's a whole lot of touch labor on aircraft that actually changes physically the geometry of the plane itself. And this kind of serialized understanding of each individual aircraft is really important to understand what mission probability success looks like. Okay, so let's think about kind of what kind of data is important. So I created this a long time ago, maybe 10 years ago. And I think some folks on the call have probably seen it before. But what you notice if you look at the red arrows from material extraction that eventually lead to disposal, and of course there could be a reverse supply chain where you're recycling some of the elements of the material. It's a fairly straightforward kind of perspective that we have a deep understanding of, and organizations have kind of built themselves around these functions, meaning that we have a manufacturing unit, we have an assembly unit, and so on and so forth. But if you look at all of the information flow that's required to connect these different material flow phases, it gets very, very complex. And, I'm not going to go into the specifics of each one of these arrows, but you just see that the information that is providing feedback to upstream processes is a lot more complex actually than even feeding, like, let's say, recycled material back to manufacturing stage. And to kind of close the gaps on this complexity, there's been a whole lot of work for many, many years, maybe I think probably like 4 decades at this point, starting in a lot of it in the late 80s, on standardizing how we pass this type of information. This is for manufacturing. This is broadly referred to as Industry 4.0 or harmonizing kind of operational technology with IT. And these are just some of the heavy hitters in the space, a mix of European standards development organizations and also American, but then also international ones. Some things I wanted to point out here is we're really interested in the Digital Metrology Standards Consortium, and I'll I'll come back to a standard that they've developed, which is all about storing quality information. Some of the contributions that we've made in the industrial AR space. So let's go back to the original, one of the original roadmaps that I showcased as one of our main deliverables from the paper. And if we look at this roadmap and think about the kinds of opportunities that lie with improving the scale of industrial XR through interoperability, we notice that that I would argue that these 4 boxes, whether it be developing new standard data protocols, linking those to automated content authoring systems, extracting features from the authoritative CAD, and adapting that based off of changes upstream. If there's a design change within the model, that should reflect itself within the AR world. You see that these are really heavy-hitting digital thread questions that are not necessarily AR-focused problems. Again, I'm just going to keep hitting that same thesis. And especially if we think about the kinds of use cases that we particularly are interested in, and there is a role in each of these for AR that we can maybe get to in the question and answer session. We need this kind of manufacturing digital thread. So these are just 3 examples. There are many more of why this is important. There's a trend within the aerospace world of realizing what's called a full-size determinate assembly, where essentially you kind of understand form to fit throughout and downstream to the supply chain for things like predicting the best time to drill a hole. And that sounds really simple, but it actually is very, very complex with the sequence of processes necessary to get the very, very tight kinds of requirements necessary for making planes fly well. The second example is this idea of understanding crack propagation through critical components. This is just, if anybody's interested, that's actually you dip parts into a fluorescent penetrant, take a scan, and you can actually visualize the crack that's propagating through a part. The reason why I mentioned that one is a lot of those technologies that actually deliver the scans, process the scans, and communicate back to those engineering authorities. Those are all separate systems, and you get into this issue of model interoperability, of actually understanding where source information came from, and that's very, very critical for God forbid, if a plane falls out of the sky and you actually need to do a deep forensic check into what actually happened and who was the one that came up with the data relevant for solving that problem. And I think a really, really massive opportunity, and this is a huge area within the Department of Defense at the OSD levels and beyond, is we are really not good at deciding what to buy early on to program acquisition. So we have a better idea of the data structures. We can actually buy them early, and so that we don't get down to all the way down into sustainment, as you see in the bottom right there, where this data becomes a lot more expensive from redoing work that could have been done much earlier in the program. So we have an active project right now where we're trying to map standards that you see in the middle there. I would just take note of them if you're interested. SysML, I'm sure everybody knows here, is a formal language for system modeling, and there's a lot of work done there for kind of requirements building in aerospace. But the basic idea is, how do we organize data in a standards-based workflow to relate requirements, and we'll come back to this and why this is relevant for AR at the end of the talk, requirements into what the nominal CAD is. That could be used STEP AP242, which is an exchange platform for CAD, but then relate that to the actual metrology that is being done, whether it be in first shot manufacturing on the production floor, or also within sustainment, meaning that the aircraft is coming for repair. What are the actual changes that were done? Where was it repaired? Where was it measured? QIF is a standard developed by, like I said before, the DMSC, the Digital Metrology Standards Consortium, for tracking results of metrology stages. So we have a very heavy effort. This is multiple projects, a programmatic plan and strategy for relating these together and then delivering a template essentially back to the Air Force and saying, this is what you need to buy early on to the effort in order to get the right kind of information to respond to significant changes to aircraft. Okay, so I tried to give that little bit of a background so that we can now talk about how these same digital thread gains can improve industrial AR interoperability. We have related efforts in this space, and happy to provide some key findings there. So this might sound like a little bit of a repeat, but I want to be clear of what problem we're trying to solve. So if you do want to develop a industrial AR scene, in my opinion, there are two kind of ways you can go. You can either basically purchase a workflow. Not to say any of these are bad, they're great technologies, but you do kind of lock yourself into a specific platform to deliver the solution at the end of the workflow, whether it be just mentioning a few here, PTC, Siemens, or Dassault, and there's other solutions there. The other is kind of rely on third-party exchange standards or translators. I'm sorry, and these are a whole bunch of different companies that have spun up to essentially construct exchange workflows so that you don't have to be specifically platform locked in. These are actually pretty expensive and a lot of hand-holding between the third-party organizations and the customer's needs. There's some interesting activity. I just listed a few here of kind of Pixies, which is that's a plugin into Unity that can read and write step files, or I guess read in step files. So we're really trying to attack what are the challenges for the kinds of requirements that we want fed into an AR scene. So hence we have this project called Quality Control Quality Assurance Companion, or QQComp for short. And this has garnered support from not only Air Force Mantech that I represent, but also Defense Logistics Agency and OSD Mantech. So it's got an interesting group of funding here. And the idea of this effort is, how do we develop a strictly standards-based workflow so that I can deliver PMI, which is that is a loaded term for, I'll just say, design requirements, things like tolerances on a machined part directly onto a part through a headset or a tablet. So we've essentially developed a database, and I'll go through that a little bit of what the goals of this effort are. And if there's interest here, happy to talk more about this in the Q&A session. So what we've done here is we've actually built in a translator that translates from your CAD data directly into QIF, which is a way of representing inspection plans that then build into the latest GLTF standard. So essentially, we have a UUID, or a universal identifier, for each design requirement that then relates directly into its spatial orientation within a lightweight model representation of GLTF. And this is backed by a database. And this database, I can just move on a little quick. This database is able to be queried and can find the related structures between, whether it be your input, which is the requirements coming out of your step file, which has all the PMI described, all the way up to GLTF. And how did we actually use this? So on the right there, you see a snippet of a website that we built that allows engineers to develop human readable work instructions that are actually authored compliant to the QIF standard. And the individual PMI that's highlighted in green and red there denotes what aspect of the part the operator is to inspect next, or the sequence of inspection plans. And the idea of this is rather than authoring the work instructions within the AR system or the AR engine, we're authoring the work instructions within a standard manufacturing structured database and then reading them into Unity to present those work instructions according to that standard. So it kind of provides this map of upstream work instruction development against presentation of those structures within GLTF. So again, it minimizes all this stuff is already happening anyways upstream to generate things like work instructions for the operators to conduct these types of metrology steps. This is just providing a means for the GLTF structure to be relevant to those work instructions, and the AR engine reads in from the database and finds those commonalities between those data formats. So that was very quick, but happy to engage offline if more interested in this particular topic. Other examples that we focused on for interoperability, on the left there, we had a project actually alongside the Lockheed group that I mentioned before, and this was a collaboration with the University of Central Florida, the VAR lab, in how do we pass common animations from one assembly to another. Think like screws, nuts, bolts that have pretty common sorts of turning type animations. The idea being authoring those over and over again with the same textures, et cetera, is just a waste of time. This leveraged the GLTF standard in sort of copying and pasting over animations. So the idea here is that the animation is defined separately from the model itself. So it's just attributed or targeted to those different parts and models. So that's actually being used right now by the EVOS team down in Orlando in Lockheed. And what you see there is, it's kind of hard to see, sorry about that, but you see kind of these red highlighted rows and the green highlighted rows. The tool itself allows you to kind of explore what are the same animations that have been preserved from one model to another. What might be an error based off of how different it is from the source model. Again, happy to talk more about that project. And on the right, I kind of alluded to this as a problem in data interoperability. We have whole different kinds of projects related to AR-assisted planning. So this is just one example of thermal coating or thermal spray. But we also have AR-assisted paint masking, AR-assisted taping. So imagine that you're trying to tape a large aircraft and you need a stencil to tape it so that you can paint properly, let's say the Air Force logo. This is just presenting or projecting that paint mask directly onto the vehicles to save time and limit the amount of steps that are required to actually produce the stencil. So we have a whole lot of those kinds of works. And of course, interoperability sits at the heart of it. I don't have a slide to show this, but I will just say that we have a lot of these projects are bespoke, created in that they want to solve, spin down, let's say 50% of time required to paint an aircraft. So those go off on their way and they develop some kind of AR solution to do that. My team kind of comes in and finds opportunity for even furthering those gains by looking at the data interoperability challenges. And my last slide is just an idea of how we can look forward and what are we looking for. And this really gives a highlight, very brief highlight of our low TRL methods. So I mentioned that we have a on-site digital manufacturing research team. And yeah, AR is one component there. The goal of this research team is really to focus on or achieve generalized manufacturing autonomy. So on the bottom right there, you see that we have all kinds of cool assets, including collaborative robots. We even have a Boston Dynamics Spot. We call it Mastro. I think that's a better name anyways. And spatial cameras or OptiTrack, system around to actually ground our truth in spatial understanding. And the idea here is how can we provide a abstraction layer that's kind of hinted on the left there with the state diagram. How can we build a data model that allows for machines, whether they be manufacturing assets like a industrial robot, but then also algorithms or digital automation agents to understand what's happening so that we can align multi-asset environments to go do tasks. And the idea there would be, again, I alluded to it on one of the earlier slides, that the goal of this gentleman trying to guide the robot on where to conduct the thermal spray, the idea there would be that you would imagine a system that would actually oversee that situation and be able to predict what does the input mean without directed knowledge or some kind of directed translation with additional human oversight and knowledge. So with that, I was very happy to present this work and happy to take any questions. Thank you.
Wow. Just, I'm impressed at how much you've done since you got to the AFRL. Okay. How big a team is it? If you're doing all this work, how many people are you? What kind of team? People are not working on this interoperability problem all the time, but stakeholders, what does that look like? Can you help us?
Yeah, so it's so I'll give the DoD answer, but I'll just say that the Department of Defense is also connected to a lot of other, I'll just say, communities. So some of these are, I would say, absent from a direct defense kind of application. Rather, they're kind of applications everywhere, all over the world. That being said, there is a Manufacturing Innovation Institute called MXD in Chicago that we serve. We serve a role there that are looking at a lot of these problems. They had a call about 18 months ago on automated content authoring, and we were affiliated with kind of that call. So I'll just say, to answer the question of how many people, that's going to be quite difficult because we have these kinds of engagements with these external organizations. The actual lab itself, we have about, I think, including on-site contractors, something like 15 folks that actually work on the manufacturing autonomy. Of those folks, I would say about a third have competency within AR, and also just like spatial registration, things that are relevant for that kind of work. And then that's just our team. So there's actually a pretty heavy kind of established competency within spatial registration across the Materials Manufacturing Directorate. Again, so the lines are not clearly drawn between kind of the AR technology space against what spatial registration means for the totality of, I'll just say, science. An example of that would be one thing that came out of the lab, I believe, like 5 years ago before I came, was called, Dream 3D. So I don't know if people have heard of that, but it's basically, I don't know if I should pull up my slide again, but it's basically a voxel rendering of a 3D microstructure. So to do that, right, you need to align a lot of material microstructure imagery, which requires a whole lot of spatial registration. So again, to answer your question of how many people, that's very, very difficult.
Sure.
We also have, I'll just end by saying, we have folks in program management roles that lead kind of the higher TRL kind of exposition. And on that team of those relevant for AR, probably about 5, but that represents a very, very large portfolio.
Thank you. I think it's amazing that Jennifer is in materials.
Yeah, absolutely.
And I mean, it's like you said materials, and you, even in your last example, Bill said, we're speaking of a fine-grained material examination. And Jennifer, you're interested in the use of AR for materials training, is that correct? Or tell us how all this fits into your universe.
Yeah, so I'm intrigued by everything that Bill's working on. I know Bill and I have worked together on a couple of things before, and it's exciting to see how worlds collide again. So I do serve as Senior Director of Education for AMP, which is the Association for Materials Protection and Performance. And so everything that Bill is sharing around the ways in which we look at how robotics and AR will help to guide human intervention with regards to what are very manual tasks right now are incredibly relevant to me. You mentioned thermal spray. Bill, obviously a lot of our colleagues across the world are engaged in applications where they are applying thermal spray and inspecting thermal spray. And so I'm intrigued by all the work that you're doing. I love that there's a human in the loop in terms of the pictures that you're showing, because there will be a human in the loop for the foreseeable future. So, I'm thinking about challenges with regards to how do we proactively prepare the workforce for what's coming around augmentation and robotics into the operational workflow. And I think, Bill, you talk about so many things that are so important, right? We have so many sources of models, of data, of human factors, hardware, even, looking at the interaction between the human and the robotics or the asset itself, right? To kind of deal with as we start to look at solutions that actually can talk to each other. And that does come from so many systems, which I think is phenomenal. I love the work that you all are doing. And from an AMP perspective in particular, we're looking at the ways in which we protect infrastructure. So all of these things are incredibly relevant to what we do and what our workforce does going forward.
Yeah, great. Yeah, happy to engage on further ideas.
Yeah. So another question from my side, are your requirements and the things that you're discovering moving into any standards groups? Are you giving your recommendations or your pain into any standards working group? You knew I was going to ask that, right?
Well, I'm glad that we planned this this talk for July and not June, because I have a good answer for July, but not June. Okay. So based off of the gains that we've made, and we realized that really the gaps that were identified, I didn't really go into them very deeply on where the problems still reside within a lot of those data structures. There's many. A lot of them have to do with the just, quite frankly, awful implementation of the standards within the software providers. And I think there's a key role that the government plays in delivering back the strong demand signal that we need them. Not you should do them, we need them, or we can't accomplish some of the ideas that I presented here today. So we just got funding for becoming a member of one of those industrial consortiums that is downstream of the standards development organization. Mm-hmm. So they provide kind of feedback, backup. We don't, though, RX, you might be interested in this, RX actually has the large, I don't know what the exact stat is. I mean, a huge amount of standards involvement, mostly on the material side. Think like ASM and these like standard material specs. We have limited engagement at the moment in some of those digital manufacturing standards organizations. So we're changing that now. We're going to join, it's called PETUS Inc., which is a implementation forum for a lot of those manufacturing standards. And not only will we, provide back where we see gaps, we're actually going to publish some of the data sets that we've generated based off of the projects that I mentioned here today. We're not members right now, but I have gotten the go ahead to join. And I think it's fair to say that other DoD agencies are doing the same. So it's
excellent. Yes, it's critical to be clear on the communications. But as you said, there are standards you could require that a provider of technology have implemented a specification, but if the compliance tests are not in place to verify that, and many standards are not written in a way that they can even be implemented, unfortunately. On our side, on the area and OMG side, we were recently acquired. Did you know about that, Bill? OMG was acquired by an organization, an industry organization, EDM, the EDM Council.
I just saw that earlier this week. Yeah.
So, so EDM is a very, very large consortium of data-centric specifications and implementations for data management. So that might be an important touch point in the future as well. So
yes, certainly. Thank you.
EDM. Okay. Anything else? Should we wrap it up? And
I think so. I've got lots more questions for Bill, but we can connect on that. And I think, Bill, you provided your connection information for others too that may be watching this afterwards, that see some opportunity and some ways for us to work on this as an ecosystem. When Christine asked the question about how many people, you said it kind of depends. I think that kind of illustrates it takes an ecosystem, right, of us all working together to achieve some of these things.
And I think one of the things that you're saying, and I hope that's happening in your organizations, both of them, is standards education. Yes. Standards, in my experience, have a very bad name, and with good reason. But we need to help people understand how they can change the system themselves from the inside, from the outside. Let's not throw the baby out with the bathwater. Just because there's a bad history and they're slow and they don't keep up with trends and they're not well implemented and there's 64 other reasons, doesn't mean that we can't be educating people about ways to improve interoperability.
Yeah, and maybe I'll end by offering another horror story. So the military is obviously very invested in standards. They need some standard way to write into contracts what they're actually buying in terms of not only the physical thing but the data, and that's they've been doing that for quite some time. We uncovered through our tech data modernization effort what was told to us as the best written contract for data ever. Okay, I'm not at liberty to say, who was it with, but it called out all the best data standards. It had down to the clauses within those standards of what kind of data elements are required to justify a good delivery of said system. And quite frankly, the prime of the contract was able to adhere to those standards because they were involved in that negotiation, et cetera. Once it got down to even tier one in the supply chain, immense pain, immense offset cost in terms of data healing, and often the program office that bought the data would just have to accept at a whim because the overrun in cost was not enough to bear the risk of losing the kind of data that they thought they quote unquote needed or required. You can imagine what that looks like once you get down to tier 2, tier 3, tier N. I mean, the aerospace supply network is quite significant. So there's a whole lot of education, of course, is very, very important. But the implementation hurdles are absolutely significant. If these things don't work out of the box, once you purchase a software that says it can export as a particular format, and it still does not conform to the intent of that standard, we're asking for things that quite honestly are just not available.
Well said, Bill. Well said.
Good job. Good job. Thank you very much, Bill and Jennifer, and look forward to the next chapter.
Okay. Thank you.
Same here. Thanks,
Bye now.
everyone.
Bye bye.
Bye. Bye.